It's a real pleasure to be here, both at HotCloud and Hot Storage. As Michael mentioned, at Berkeley we've been building something called the Berkeley Data Analytics Stack. I'll get rid of any of the mystery right now. It's pronounced badass. And it turns out that a number of the key components that we've built in the badass stack were first introduced at the HotCloud workshop. So when I was invited to come and address you guys, I took advantage of that opportunity. So what I want to do today is really spend a bunch of time kind of walking you through the stack, telling you a little bit about what we've built, why we've built it, and how we've built it. And then towards the end of the talk, sort of turn a little bit more towards, looking forward, thinking about interesting new challenges, both ones that we're looking at in the lab right now, as well as, just other challenges that I think this particular audience would be, the right people to be thinking about, and hopefully you're already thinking about a lot of them. So, so it's a big data talk, so I need to start off just saying a little bit about big data. And, I'll give you our particular spin on it, but, basically these are the four places that we see large volumes of data coming from. And if you sort of start in the left and go clockwise, all the online activity just generating huge amounts of log records, companies that you've never heard of, don't even know that exist, get involved when you look at a web page, click on an ad, watch a video, and just cascades of information gets generated every time anyone does anything online. So that's where a lot of the information that's driving the big data revolution is coming from. But there's also other types of information. There's user-generated content, a lot of excitement about Internet of Things and machines, machine-to-machine communication. And what's interesting there, of course, is while the top two are sort of somehow proportional to the number of people in the world and the things that those people are doing, machine-to-machine communication, of course, isn't limited by that. And so there's the potential for much larger data volumes in the long run, looking at Internet of Things. And then finally, something that drives a lot of our work is really what's going on across all the sciences. And really, if you look across a large campus, like Berkeley or really any large campus, what you'll see is that many traditional science disciplines are turning into data-driven activities. And so you collect a lot of data, and then you analyze that data to find interesting things that are going on, to come up with new hypotheses, and so on. Now, this graph that's probably hard for you guys to see, basically it's a log scale. This kind of boring straight line, that's Moore's law. So, things getting better by a factor of 2 every 18 months. This line that's just dropping like a rock, that's the cost of sequencing genomes. So if you're a geneticist, if you're working on genomic data, your computers are basically getting that much slower every year. And so just huge volumes of data being generated. So, the reason that there's so much excitement around this topic of big data is really because it spans all these different areas, really spans almost everything you can think of. Now, something that we found helpful to think about, what do you need to do to address big data analytics, is a pattern that I've seen over and over again. And, people try to define big data, it's bigger than you can handle with traditional technology. There's a bunch of different definitions. This is more of an example, I think, that I find illustrative of what you can do with big data that maybe you couldn't really think about doing before. And so this is an application we built in the lab. It's called Carrot. And what Carrot does is it runs on your smartphone. And it just watches what applications you're running and what happens to the battery on your phone, periodically uploads that to the cloud. And we have an application that's running on Amazon Web Services, and it's basically just collecting all the data from all these phones, and it's building models. And the trick is that if you look at any one phone, you can learn some things, but it's not particularly interesting. But if you look at lots of phones, you can start to detect really interesting patterns. So for example, you can tell over a large population how certain applications use the battery on certain devices. And then what that lets you do is you're collecting all this information from individuals, you're aggregating it, and then you're using what you learn from collecting from those individuals to give back personalized recommendations. So we can tell you, oh, well, you've got a particular device running a particular version of an operating system. Well, it turns out that Google Maps is known to be a battery hog on that device with that operating system. So looking at your phone versus all the other people who have a similar phone except that don't run Google Maps as much as you do, we predict that if you stopped running Google Maps, your battery would last an extra hour and a half a day, right? So you can find patterns like that. Or you can find outliers. So you can say, gee, Skype on your phone seems to be correlated with high battery drain, but most people that have your phone don't have that problem, so maybe you should uninstall Skype and reinstall it. Okay, and so what's going on here is by collecting lots and lots of information, you're able to find these patterns, you can find the normal trends, you can find the outliers, and then you can turn around and use those to make personalized recommendations. So, battery life on your smartphone is one application, and this application we built, caught on pretty well. It's had almost 1 million downloads by now, so we're getting some really good information from it. But you can obviously things like personalized advertising, personalized content. It's a little glib, but you can think about personalized medicine having a similar pattern. So when you think about big data, yes, think about petabytes and yottabytes or whatever your favorite prefix is. But there's something more to it than that. It's really the idea that once you collect a certain amount of data, once you've gotten over some critical mass of data, you can learn things that you can't see when you're looking at smaller data sets. And that's what's interesting about it. Okay, so that's one way to think about the big data world out there. So another way is, when we're designing our systems, we've really been looking at the big data analytics problem as basically you're trying to answer a question or you're trying to make a decision, and you need to do that within this envelope of you have a certain amount of time to process the data, right, and you're going to make your decision. You've got a certain amount of money you could spend on processing, and you need a certain confidence in the answer so you can make your decision or you can decide that you're done, okay? And in some sense, the challenge is how do you solve the problem, the data-driven problem you're trying to solve, and stay within this envelope. Okay, so as the data grows, as data gets more complex and diverse, it gets more challenging. And so then we do the things that we as systems people like to do. We try to figure out how to make the system go faster. Okay, so you scale out. You figure out how to make things more efficient. Okay, and you can do that for a while, and I'll tell you how we've done that for a few key use cases. But at some point, you're going to run out of gas. Okay? And if the data keeps growing, so think back to that genomics graph that I showed you a couple slides ago, right, where it's just, the rate of data generation is growing so much faster than computers are getting faster. At some point you hit a wall, and then you need to be thinking about doing something else, which is you start to think about trading off amongst these different parts of the envelope. Okay, so you say, okay, well, if I'm willing to accept a slightly less confident answer, I can get a quicker answer. Okay, or if I'm willing to spend a lot more money, I can get a better answer. Right, so you can basically trade off among time, cost, and quality. Okay, and so another kind of view of the big data problem is this one here. How do I run as efficiently as possible so I can answer the biggest and most interesting questions with the resources I have, right, with the requirements I have. And then once I hit a wall, can I intelligently trade off across these three different dimensions to solve my problem? Okay, and at a high level, that's a big part of the research challenge. All right? So, as Michael said, what we're doing in AmpLab is we're saying, all right, the way to attack this problem is to think about the resources you have available to make sense of data. And we identified 3 of them. So algorithms, so thinking about machine learning, statistical methods, business intelligence types of processing and so on. The M is machines, so the reason we're here, cluster computing, cloud computing, warehouse scale clusters and so on. And the P, as Michael mentioned, is people. And you can think about people in 2 different ways. Certainly as individuals who are interacting with the system and trying to understand what's going on in the data, so you need to think about visualization and mixed mode, mixed initiative interfaces and things like that. But kind of more interestingly, or perhaps more interestingly, is the opportunity to take advantage of all the people that are connected on the internet through crowdsourcing platforms like Mechanical Turk and others. Okay? And if you think about it, that's a resource for processing data too. All right, so what we're doing in the AMP lab is trying to say, okay, how do we build a system that integrates these 3 very different types of resources to solve the big data problem that I just outlined? Okay, now, where does this fit in with some of the things that we're focused on in these workshops? Well, if you think about it, this is an incredibly dynamic and elastic environment. So start with machines, right, because that's the one that's sort of most natural. Obviously, cloud computing, brings elasticity, multi-tenancy, brings a lot of dynamism to systems. Increasingly deep and flexible and dynamic storage hierarchies, brings a lot of change and elasticity, and then different models of consistency let you do certain types of trade-offs. Okay, so clearly on the machine side of the world, we've got all sorts of flexibility and elasticity. But we also have that on the other resources as well. So in terms of algorithms, there's a huge amount, huge libraries of machine learning algorithms that all have different properties that are good at different things. Often the right answer to a particular machine learning problem isn't a single algorithm, but it's a combination of algorithms through something called ensembling. There are techniques for active learning where the behavior of the system adjusts based on the need of the system. And as we'll talk about a little bit later, we can also give approximate answers. So that's another knob we can turn. Okay, so there's a lot of flexibility on the algorithm side too. And then on the people side, of course, doing anything with people, either individually or in groups, always introduces a lot of uncertainty and a lot of change and churn. And so especially if you look at trying to do any real processing in an environment like Amazon Mechanical Turk or anything like that, you'll see that it's a very hard environment to program reliably. Okay? So if you look across all 3 of our resources, huge elasticity, huge potential for flexibility and change, and scheduling problems, resource allocation problems, correctness issues, all these things. Okay? So really, in a nutshell, if you think about it, this is a pretty good research challenge, right? There's a lot going on here. Okay? We're trying to integrate these 3 very different types of resources, right? Algorithms, machines, cluster computing, and cloud processing, people, individuals and groups, all right? So we've got these 3 very different types of resources we can push on. They're all incredibly flexible and varied and, hard to program, frankly. We've got this other set of trade-offs, right, where we can trade off time versus cost versus quality. Okay, and we have a lot of intelligent decisions to make there. And of course, the better we do, the more things people want to do with our technology. So the questions people are asking are getting harder. The applications people are trying to support are getting more sophisticated. Okay, and so when you add all this up, it's a great research topic. Okay, and so yes, there's a lot of hype around big data, and it's easy to dismiss it. But there's a real fundamental reason why it's so important in research, and it's because all of these are just full of open questions. Okay, and especially when you start trying to put them together in a system, it's really not clear how to do it. Okay, so one main takeaway from this talk is really this: that if you're trying to understand, what does the big data movement mean to me, this is one slice of that. Okay, all these challenges. Okay, and this is what we live for, right? This is why we do what we do. Okay, so let's talk a little bit, or maybe a little more than a little bit, about what we've been doing at Berkeley. And so we built this thing called the Berkeley Data Analytics Stack. And the best way to think about it is the following. This is always hard for me to say. Michael didn't actually mention this, but I'm a database guy by training, and did a lot of my initial work on parallel database systems. And if you look inside a parallel database system, you'll see an engine that basically can apply operations to individual items and then group those items. Okay, that's kind of what's at the heart of any parallel database system. It's been there for decades. But this field really took off when the Google guys published their paper on MapReduce, which was a sort of a more open platform, a generic platform for doing processing across clusters. And then maybe equally as important, or maybe even more important, is a group of people built an open source version of this called Hadoop MapReduce. And that's what really caused this cluster computing area to take off. Okay, so great. So MapReduce was a general batch processing system. You could, do PageRank. You could, use it for data cleaning and so on. But what happened was people said, well, this, MapReduce is cool, but I've got a bunch of things I want to do. I've got graphs I want to process, right? I've got SQL queries I want to run. I've got streams I want to process. And so what happened was people said, okay, well, I can take this fundamental MapReduce idea and I can specialize it, okay? So I can come up with a version of MapReduce that works for graphs, or I can come up with a MapReduce-like system that does some sort of streaming, all right? Or I can even build an SQL, query processor on top of it, okay? So there was this kind of explosion of new and specialized systems that were each targeted for some, for some design point, all right? And this is really where the big data ecosystem, has gone. So our approach in Badass has been different. We said, okay, well, let's not specialize MapReduce. Let's see if we can generalize it. Let's make it a little bigger, and then see what we can do with it. So, it turns out, and a lot of this was work that Matej Zaharia did that was presented here probably 4 years ago now on the Spark system. But basically, the idea is that if you add the notion of general DAGs, right? So not just maps and reduce, but more elaborate computational structures, okay? And you allow data to be shared across the different steps of your computations, all right? That is going to be enough to support all those different models that we were talking about. So you can do streaming, you can do SQL, you can do graphs, you can do machine learning, okay? And the idea is that, if you're a user, there's going to be some potential advantages here. For one thing, you don't have to use a different system every time you've got a slightly different view of your data. Okay, and the truth is, for a lot of complex applications, you have data that you want to look at as records, and then you want to look at it as a graph, and then maybe you want to stream that data. Okay, so basically there are just different ways of looking at the same data set. If you have a bunch of specialized systems, you've basically got to copy data, from one to the other. You've got to run all those different systems. You've got to figure out how you're going to allocate your resources across those different systems. Okay? If you can do it all in a unified system, you don't have those problems. Okay? So, fewer systems to use, fewer systems to learn, fewer systems to manage. And then, you're not copying data necessarily all over the place. So there's some performance advantages. All right, so from a user, that's kind of what you get. That's the view. In terms of development, this is kind of an interesting set of graphs. Basically, let's see, I don't know which way to look. If you look here, this is lines of code. So this is Hadoop MapReduce. This is Storm, which is a streaming system. Impala, which is Cloudera's SQL system. Giraffe, graph processor. Mahout, which is a machine learning library. And then Spark, which is sort of our core execution engine. And what you'll see is, first off, Spark is, the core of Spark is pretty small. And partly that comes from the fact that it was written in Scala, which lets you write very tight code for these sorts of things. But what's interesting is, then you start saying, okay, well, I've got Spark, and that does basically what MapReduce does. It does a little more. Okay, but then I can layer in streaming, and it costs me that much. And then I can put on SQL, and it costs me, a bit more. And then I can put in graph processing, and then I can put in machine learning. Okay, so by being able to leverage a common core of functionality, you can build a much tighter system. Okay, so from the user point of view, there's the advantages of one system. From the developer's point of view, there's a lot of shared, you avoid a lot of duplicated work, let's say. Okay, and of course there's a small trick of making it perform as well as each of those individual systems, and we can talk about whether we've actually been able to do that or not. Okay, clearly, there's a chance that you'll have to give up something. Okay, and so the question really there is, how close does your performance have to be to that of a specialized system to make it worth just using the unified system instead of a bunch of different specialized systems? Okay, and so we'll talk about that. Okay, so in the project we've made a few bets. Some of them maybe look less controversial now than they might have been when we started. But we said, okay, we're not going to buck the trend, in terms of commodity processing. So we're going to use commodity processors. We're going to use, elastic compute like you get in a cloud infrastructure. We're going to do in-memory processing. We're going to use scalable storage like you get with the Hadoop file system. We're going to optimize for these different common patterns. We're going to treat them as views of the same data. So machine learning, graphs, queries, MapReduce, matrix libraries, and so on. We can build all that on our system. And we want to optimize for each one of those. We're going to look at trade-offs, as I said before, between accuracy and runtime and even cost. So we're going to use sampling to do some of that. We're going to have relaxed consistency when that's the right thing to do. I already made the case for integration. We're going to try to put all these systems onto the same substrate, and we're going to support different modes of interaction. So batch processing like you get with Hadoop MapReduce, stream processing, being able to act on the data as it's arriving, and interactive, just being able to get answers that return while you're sitting there, as opposed to an hour later or a day later. And the other thing that we've done that's turned out to be quite important is from the very beginning we embraced the open source community, and all the work we're doing on the Badass Stack has been going into open source. Okay, and so we'll talk about that a little bit. But it's from our perspective as university researchers, that meant that our students really, who do all the coding, had to sign up for doing stuff with a certain amount of quality, right? And we were going to, if you put stuff out there, it's got to work reasonably well, okay? And so everyone bought into that, and that's extra overhead. It keeps you from, it keeps you from writing more papers potentially, okay? So, all right, so this is what the stack looks like, and you got to read it kind of bottom up. But at the bottom is resource management. I'll talk slightly about that. One up from that is the storage layer. The hot storage people will be disappointed about how little I'm going to talk about that. I'll give one slide. And then we talk about processing. So the Spark engine I'll talk about, and then the different views of the data that we've put on top of that. So at the lowest level, just one slide, we built a system called Mesos. This actually predated the AMP lab. It was done in a previous project called the RAD lab. And the idea of Mesos is really, it's a cluster virtualization layer. I think it's fair to say that its design influenced the design of Yarn, which came a little bit later. But there are some technical differences between them. But the idea is that you should be able to share a physical cluster across multiple different software frameworks, and that the sharing should be done in a way that the resources are shared fairly and efficiently. And Mesos has been quite successful. The most vocal user of it is Twitter. They stopped announcing how many servers they were running it on, but they were over 10,000 last time they announced it, and they've got a large portion of their engineering team running jobs on it. So, again, university code, but having a real impact. And since then, because we're in the open source world, a number of companies have stepped up and added schedulers to it. So Airbnb and Twitter have done this. And then a company spun out recently called Mesos, which is commercializing it. Okay? So, sort of at the lowest level, just think about having a virtualized cluster. Okay? So when you want to run your framework, you get a private cluster. That's what Mesos gives you. Tachyon, which sits on top of that, is a newer part of the stack. And really what it is you can think of it as a caching layer for HDFS and other types of networked and distributed file systems. Okay? And so the idea is it keeps things in memory. That's going to be one of the big things that we're going to get our performance boost from. And it does so in a fault-tolerant manner. Okay? So it takes care of replication and recovery and things like that for you. And the idea, and again, as a database guy, I'm a little embarrassed that I didn't catch this at the beginning. But Spark, each Spark job runs on its own instance of the JVM. So when you're creating data in one instance of Spark, it can't share that data with other instances of Spark, which is, again, database 101. You wouldn't do that. You would build a shared buffer pool and share it that way. Tachyon's basically that shared buffer pool. So we've taken the storage abstraction out of Spark, right? We've made it its own part of the system. And so now multiple frameworks can share the same data, whether it's different instances of Spark. You can have Hadoop MapReduce use the data and so on. Okay. And so what Tachyon gives you is shared data. Because we're running in the JVM, we have to worry about allocating things off the heap. Otherwise, you get killed by garbage collection. So it manages off-heap allocation of storage, and it has it's compatible with HDFS. Red Hat is supporting it now for one of their file systems, and so on. So, a little disappointing for the hot storage guys, I realize. If you have questions about Tachyon, I can try to answer it. But the basic idea is, it's a shared buffer pool for the badass stack and other things that want to use it. Okay? So that's kind of the bottom two levels, right? Mesos, which is resource allocation, Tachyon, which sits on top of HDFS for storage. Okay? And then I want to start moving up the stack. So let's talk about Spark. Because that's kind of at the heart of it. And, getting a little bit ahead to the punchline, the open source approach has been tremendously valuable for us. Spark, which started off as a student project in the lab, has kind of taken on a life of its own. And this is an article from earlier this year that basically a number of people are predicting that, MapReduce is going to fade away as a key tool in the big data ecosystem, and Spark is looking like one of the leading contenders for what's going to replace it. Okay, which is pretty nice for a student project. So Spark just released. Oh, okay. So I should mention about a year ago we donated Spark to the Apache Foundation because we wanted to let it grow to beyond what we could handle in the lab, and they just released the version 1.0 of Spark, which includes a bunch of things I'm going to talk about briefly. The Spark itself, the streaming version of Spark, the graph engine that runs on top of Spark, machine learning libraries, and so on. And it's got different interfaces. You can get to it through Python, through Scala. There's a shell for R, which is a statistical language. It's quite popular among many data scientists, and of course through Java. Okay. And so, the 1.0 designation is meant to be important. It's a big step in the maturity of the system. And, part of the community building of this thing, we've been running meetups in San Francisco for years. I think a group has started in Boston. A group has started in Hyderabad. There's a Spark Summit in China. There's a Spark Summit in Tokyo coming up. Spark is now a big part of the Strata conferences that O'Reilly runs. So the community has been growing and expanding. 1.0 has about 180 different contributors from 30 different companies. And this graph here, in terms of contributors, is basically showing that Spark has sort of outpaced Hadoop MapReduce in terms of the size of the community that's contributing now. Okay, and just for scale, the lab has about 30, 35 graduate students. Okay, so we're getting 6x at least from that. Okay, so that's again part of the power of open source. It's catching on in industry. There's a company that spun out of the lab called Databricks that's kind of leading the charge on Spark in the commercial world. All the major Hadoop distributions include it now, and there's more and more announcements coming out. DataStax just announced an integration of Spark with Cassandra. There's other things like that happening, on a weekly basis, really. Okay, so what's Spark? Some of you might have seen this. As I said, Spark was initially presented, in the HotCloud workshop in 2010, I believe. But here's what Spark was set up to do, and it's interesting. I mean, I'll just mention the story briefly. As Michael said in the introduction, part of what the AMP Lab is trying to do is bring together people with very different research agendas and different levels of different areas of expertise. And so we've been really successful with getting core machine learning people to sit with systems people and really work together. And one of the first big successes of this was the Spark system. And the story goes like this. The machine learning people were trying to run an iterative machine learning algorithm on MapReduce, and it was running slowly. And so they went over to the system side of the house and they said, hey, can you, help us debug our program? Why is it running so slowly? What are we doing wrong? And, systems folks looked at it and they said, no, you're not doing anything wrong. This is the way Hadoop MapReduce works. And so what was happening is they were running an iterative algorithm, and the iterative algorithm, you start off with, you have a set of training data and you want to train a model. So you start off with an initial model, and you run it through the MapReduce pipeline. So you map it, you reduce it, and then you write out your model. Okay, and you come out with an initial model. And then what you do is you iterate over that model to try to improve it. So then in the next iteration, what happens is you do the same thing. What MapReduce would do is it would read the training data in all over again. It would map it, reduce it, write out a model, iterate again, and so on. Okay, so basically every iteration was loading the data from disk, okay, and was saving out a whole bunch of data in between stages, or basically communicating from iteration to iteration through the disk, which I don't think I have to tell you is about the slowest way you can communicate between two stages of a process, right? So when you look at that, you say, okay, well, clearly what's happening is that Hadoop was not designed for this use case, right? The reason Hadoop uses the disk so much is because it was designed for providing fault tolerance in very, very large-scale systems of unreliable nodes, where the assumption is that during any computation, you're going to have some nodes fail. And so what you do is you write out data to the disk, whenever you can, so that if something fails, you can pick up the pieces and recover, okay? So, this was a case of people kind of getting ahead of the technology. The technology had certain use cases in mind. People wanted to push the envelope there, and when they did, it didn't work as well. And so, so you look at that as a system person, you say, okay, well, clearly there should be a solution for that, and the solution should be I should figure out how to keep things in memory. So that's what Spark does. Basically, you process your data, you cache it in memory, and then what that lets you do is for each iteration, you're now serving it out of memory, not off of the disk. Okay, and that's obviously going to be a lot faster. And then you also enable more complicated task structures, so that you don't just have to do MapReduce, MapReduce, MapReduce. And so then you can close a loop between your iterations as well. So basically take all that disk processing out of the critical path if you can. All right? Now, if you're paying attention, you're thinking, okay, well that's great, except I just lost all my fault tolerance, right? Which was the whole reason I was dealing with the disk in the first place. And that was really sort of the key thing that Spark figured out, is said, okay, well, how are we going to provide recovery? How are we going to provide fault tolerance in this environment without using the disk so much? And the answer was an abstraction called Resilient Distributed Data Sets, RDDs. And what's interesting about RDDs is really two things. One is that they're immutable, okay? So you create an RDD, and then it doesn't change, okay? So it's easy to recover. And then to process an RDD, what you have to do is you have to transform it to a new RDD with one of or some of a small set of transformations. Okay, so coarse-grained transformation. Create an RDD, transform it into a new RDD. And what this is going to let you do is it's going to let you keep track of the lineage of any piece of data in your system in a very succinct way, okay, so that you always have the recipe to recreate any piece of data you've lost, okay, and you're not paying much overhead during normal processing, okay. But the trick is, though, is that this simple interface, right, it's one of these beautiful kind of systems abstractions that's kind of just at the right level, that, immutable data sets distributed across the cluster with the right set of transformations lets you implement all those different systems that we were talking about before. So you can build graph processing on it. You can build SQL query processing on it. You can build streaming on it, okay? And so that's really what's at the heart of Spark. This is the set of operators that you get. So you get map, you get reduce, and then you get all these other things. So when I talked about generalizing map reduce instead of specializing it, this is what I meant. Okay, so you have map, you have reduce, and then you add functionality to it. All right, and this is just a sampling of, this is actually most of the operators you can do on RDDs. Okay, and you can see, it warms my heart. You have things like, join and, filter and group by and things like that that make a SQL processor happy. Okay? All right, so then how do you make that work fault tolerant? Well, I sort of already told you this. Basically, since RDDs are immutable, and you can only create new RDDs through this very limited language, what you can do is just track the lineage at a very coarse grain. So this is basically taking a text file, it's filtering out some of the lines, and then it's splitting out some of the words from those lines that survive the filter. And you can create the lineage that just looks like this. It says, I started with an HDFS file, I read it into memory, I filtered things out using a predicate, and then I split each of the lines that survive the filter. Okay? And that's enough information, along with the original RDD and a map of where the pieces are. That's enough to recover any piece that fails along the way. Okay? And then, of course, there's details, right? Because you don't always want to have to go back to the beginning of the lineage, so you want to do checkpointing and things like that, but you do it in the background. It's not in the critical path anymore. Okay? So that's what Spark did. Okay, once you have that, you can add streaming to it. I'm not going to say much about streaming, other than it was presented at HotCloud a couple of years ago initially, recently came out in SOSP. But the idea here is you, at least in the way Spark does streaming, is you split the incoming data into chunks, and then you process the chunks individually. This works for a lot of things that you want to do with streaming. It doesn't necessarily work with everything you might want to do with streaming. But the basic idea is, it's a little hard to read, but if you wanted to count words from a file, let me go back, sorry. You kind of read the file, and then you apply the split function to it, and then you count the words. You do basically the same thing in a streaming world, except now what you do is you open a socket, and then you tell the system, hey, every 10 seconds, run this program on the data that came in. And what's cool is if you look at the program, it's pretty much identical to what you do in the batch program. Okay, so it lets you move back and forth between batch and streaming. Okay, so again, that's part of the philosophy is build one substrate for these different modes of interaction. Okay, so that's Spark streaming and Spark. Let me say a little bit about SQL. As a database guy, I have to say I enjoy this, but if you look at what's going on in the Hadoop world, one of the main things that's going on in the Hadoop world, which was originally called the NoSQL world, is SQL. Because it turns out that SQL is a pretty good language for doing a lot of data analysis that you'd like to do. And so there's a bunch of activity now, if you look out in what's going on in the big data space around what people are calling SQL on Hadoop. Okay, and we're one of the groups that are doing it. We have a thing called Shark, and basically Shark lives on top of Spark, and so if you remember that example I showed of the machine learning case where every iteration was reading the data in from memory, if you build a query processor on Hadoop, like say Hive, it does the same thing for queries. Every query you run is going to bring the data in from the disk again, just like the worst possible way. I mean, it just kills me. It's the worst possible way to build a database system, okay? And so we're able to leverage the in-memory processing of Spark to avoid that problem. It's not rocket science. So we took Hive, and what we're able to do is quite cool. We, because it's all open source, right, and that's, again, one of the big themes of this talk, is we're able to take the Hive query processor and modify it. So you can run Hive queries on our system, okay? And Hive very nicely provided a metadata catalog that's open source. And so we use their metadata catalog. And so you can have data that's stored in Hive, and you can run Shark on it. So your existing queries work, your existing data works. You don't have to reformat anything. You just have to recompile your queries, and then you can run. And things can run 10 or 100 times faster. So not surprisingly, it's gotten a lot of traction. And so, what we've done in this first version of Shark is we've taken Hive, which has, this is the catalog for telling you what your tables look like. Here's Hadoop MapReduce and the file system down here, and here's all the guts of the query processor. And, basically, we replace the guts of the query processor. We replace MapReduce with Spark, and, you get this query compatibility and data compatibility, okay? It's the beauty of open source. Now, there's a new version of Shark coming out. There's something kind of hidden. It's actually not hidden. It's just inside of Spark version 1.0 called Spark SQL, which is a more native SQL processor. Right now, Shark sits on top of Spark. So this is inside of Spark. But we're going to be porting Shark to this new query processor. So, if you have existing Shark systems, they'll still work. And I'm not going to show many graphs, but this is one benchmark. This is a simple scan, and the thing to see is if you compare Shark to, this is Hive and Tez. So, Hive is, this is running time, so upper is worse, right? You want to be low on this thing. And, the green is Hive. That's the thing that everyone likes to beat up on. Tez is the new version of Hive. It's kind of twice as fast. Impala, which is to the left of our stuff, is Cloudera's SQL system. And then the thing all the way to the left is a relational system called Redshift that Amazon hosts on their cloud. And the bottom line here is that there's a bunch of systems that are sort of competitive. Okay? The relational system, at least in this case, is a little faster. It's tuned for the hardware that it's on. There's some reasons why that might be. But if you look at Impala and you look at Shark and you look at other systems like that, they're all going to be pretty competitive. We win sometimes, they win sometimes. And what's beautiful about open source is if we're losing, we can look and see why and then take those ideas and put them in our system, and they do the same to us. And so, what you're going to end up with is sort of a race to the bottom of this graph, which is where you want to be. The community is able to innovate. And so, this gets at that question I raised earlier of, if I build this omnibus system, right, the system that does all these different things, right, the Swiss Army knife, is it going to be as good as a purpose-built system? And the answer is, it's going to be pretty close. And that's interesting, right? That's interesting. Another integration, you can put SQL into your Spark code. So this is a SQL query that's embedded in some Scala, and then once you have it in an RDD, you can then run your machine learning on it. So this is logistic regression, right? It's a clustering algorithm. Okay, so just showing again, so you can switch SQL to Scala, Scala to machine learning. I'll show you quickly something about graphs and so on. what we're doing in terms of trade-offs among, for accuracy and speed, I'll just mention quickly, we have a system called BlinkDB that basically lets you ask SQL queries and then say, give me the answer within a certain amount of time, and then give me error bars on that answer, right? Or, run the query until I have a certain level of confidence and then stop. Okay, and so what you end up with a system like this is, you can run the query on all the data, you can run the query on 10% of the data, or 1% of the data, or 1,000th of the data, and you'll get error bars on that. And depending on your query, of course, the errors can be quite small. So in this particular query, you're running 10 times faster, and you're getting a 0.02% error. Okay, and so so this is all based on sampling. BlinkDB pre-computes a bunch of samples. There's a bunch of statistical magic that goes into deciding, how to do that sampling. And then there's a whole other set of statistical magic that goes into computing those error bars and then convincing yourself that the error bars themselves are accurate. There's a paper in the upcoming SIGMOD next week on how those error bars are calculated and validated. Okay? But this is a key thing I just wanted to show you, is you can get tremendous speed ups if you're willing to give up a little bit of accuracy. Okay? And, for a lot of things that you want to do, especially when you're first doing, if you're doing exploratory data analysis and just trying to figure out what's in your data, this is the way to do it. You don't need to run 3 hours to get, to get down to the 10th decimal point, right? You just want to get an idea of what's going on. All right. So I was going to tell you about graph processing, but I think I'm going to skip ahead on that. But if you're interested, we have a system called GraphX, which basically what it does is it stores all the graph information in tables, right? So you have a table of vertices, you have a table of edges, you have a mapping table, and then it's got optimized, basically treats join traversal as a join, graph traversal as joins, and then we have highly optimized joins to make that run fast, okay? And if you're interested in graph processing, just catch me after. I can tell you more about that. So we're doing a bunch of other stuff in the lab. We've got projects on machine learning and trying to make machine learning easier to use. That's called MLBase. We're moving in the direction of handling updates. So I said that the key of Spark was these immutable RDDs. That's great for certain things, but they're immutable. They're hard to, you can't update them. So that makes it hard to do transactional stuff on. So we're doing a bunch of stuff on transactions and looking at what's happening in the data center in terms of different storage hierarchies, cold storage, trying to understand what the memory hierarchy looks like in the data center, and then looking at where hardware is going as well. So looking at exploiting GPUs and things like that. So let me just take a couple minutes and just wrap up and sort of tell you what I think is going on here. When people think big data has this problem, it's got a bunch of problems as a term, but one of the problems is it's got this word big in it. Okay, and big sort of, for one thing, gets people on edge because you have to say how big is big. Okay, and I talked a little bit about that at the beginning. But the other thing is it makes you think that the whole issue is about scalability. And it's not really about scalability. As I said earlier, there is this tipping point where when you've collected a certain amount of data, you can see things that you can't see if you had less data. So that's true. Okay, but if you look at the software, if you look at the ecosystem that's being built, right, if you look at Hadoop and you look at Impala and you look at Spark and all this stuff, what's really going on there? And yes, scalability is interesting, but it's not just about that, right? Because you can make a parallel database system scale. I've done it. You can do it. It's not really about speed, right? Speed's important, but again, you can make traditional systems run faster. We know how to do that. What it's really about is it's about flexibility, okay? And this is the key thing. This is the difference. So the world I grew up in looked like this. You would collect data from applications, from various places, from logs. You would run it through this process called ETL, which is extract, transform, load. So you basically take the data and you'd squeeze it into a schema. You'd clean the data, you'd format it properly, you'd structure it properly, and you'd stick it in this vault called a data warehouse or a database, okay? And that's the way business intelligence, that's the way data analytics at most enterprises was done and frankly still is done, okay? Now, the trick is the big data ecosystem has kind of exploded this. Okay, you don't have to do it this way anymore. So if you're a database person, this is the way the world looks. You've got storage, you've got some processing layer, you've got SQL. Data comes in this way, and data comes out that way. So there's one way in and one way out. So when you take a traditional relational database, the system makes you a promise. It says, if you give me your data and let me lock it up and do whatever I want to it, so you can't get at it anymore, I guarantee I'll give you efficient queries and I'll protect the data. I'll make sure it stays consistent. Okay? And the price you pay for that is you lose access to your data, except through that one way in, which is SQL. What the Hadoop Stack did is it split that up. So it's like, you know, you've got a file system at the bottom. You can read data from the file system if you want. You can write MapReduce directly if you want. You can go at structured data if you stored it with something like HBase. Or you can get at it through any one of these higher level languages, including things that look like SQL. Okay? So this idea of taking the data and locking it away, putting it behind this wall, that doesn't exist anymore. You can get at the data at whatever level you need to get at it. Right, which is important, because sometimes, right, and we learned this is like the SQL irony, right? Sometimes SQL is exactly what you want. So great, use it. But sometimes you need sometimes SQL doesn't let you do what you need to do. You want to do some sort of machine learning algorithm. You want to, you know, get at the actual bits and bytes. Then you can go lower. You can do something else, okay? So that's one key example of the flexibility that you get. You know, the other flexibility you get is from this idea of schema, right? So remember that ETL process was, I'm going to structure my data, I'm going to take incoming data, I'm going to figure out what it looks like, I'm going to convert it, and then load it, right? So extract from wherever it was, transform it, and then load it into my database. That's got some advantages, right? The advantages is when you read it out, you can read it fast because it's kind of pre-compiled, and you can put standards and governance on it, right? Because you know what the data is supposed to look like. But the problem is it's this huge roadblock for ingesting new data. And what's happening in the big data space is the opposite. People are saying, hey, just throw the data into the system and figure out what it looks like later. Okay, so sometimes that's called schema on read, sometimes it's schema never. Okay, but it's a fundamental difference. And what it lets you do is, you know, traditional data warehouse projects have always been, had this risk of this huge setup time, right? It can take months or years to design your data warehouse and finally start loading data into it, where in this new world, you can just start throwing data into the system and you can get value right away, right? And that makes things go a lot faster. And so what's happening is that ETL is becoming more of a continuous process. It's not an upfront thing you do that you have to do before you can use the data, but it's something you can do as time goes on. You can improve the quality of your data. Okay, so this is important as well. Okay, something else we're doing in the lab, this is a complicated picture. I don't have time to go into it, but you know, we're looking at this problem of random reads to data, which frankly Spark is not that good at, and random writes to data, which Spark doesn't let you do at all. And what that's going to allow us to do when we add that functionality to the system, it's going to allow us to build a system where you're constantly updating models. So if you think about having you know, models, say you've got a bunch of users and you're trying to model what those users are doing, you can now update your model for each user in real time as that person is using the system. Okay? And so we're looking at how do you integrate serving of data and models into a stack like the existing analytics stack that we have. Okay, so you know, how do you integrate serving and analytics? So these are the things that I'm thinking about, and I'll just leave you with this stuff. So one is this idea of, okay, you know, analytics is great, but we know we want to do serving, so how do those things interact? Traditionally, they've been two different systems, your transactional system and your analytics system. Is there a way to fix that, or is it always going to be that way? We're going to try to fix it, because we're doing university research, we can take that chance. I don't know if you want to start a company doing it or not, but you know, for research, it's a great research topic. In the whole kind of big data ecosystem, people have largely not worried about single node performance, right? And my view is if somebody tells you they're running, you know, a 10 node Hadoop cluster or maybe a 20 node Spark, I'm sorry, I said a Did I say it right? Sorry, a 20-node Hadoop cluster or a 10-node Spark cluster, they could probably do that on a single machine. So, we really need to be thinking about, on a single machine, how do we take advantage of huge memory? How do we take advantage of, multi-core? How do we take advantage of let's not worry about building distributed systems if we don't have to, because we all know that distributed systems are harder. So single node performance. If you start looking at Internet of Things, there's this natural tendency to want to push the processing out to the edge where the data is being collected, right? Because we've learned that pushing computation to data is typically more efficient than trying to keep pulling the data to the computation. But that adds a lot of complexity, right? Because you've now got computation spread all over the place, and you've got to manage that and make it efficient and fault tolerant. And then, as always, there's huge changes going on, with individual servers and across the data center in terms of processors and communication and so on. So you got to keep an eye on those. So this is really the direction that we're going in. So just to wrap up, and our view is that if you want to crack the big data problem, you've got to figure out how to integrate algorithms, machines, and people. We're building the badass stack as our main delivery vehicle. Doing it through open source has given us leverage that we would have never had, even as a fairly large academic lab. Open source has just given us access to companies, to programmers, to use cases. It's just been a great way to do it. What's going on in the big data movement now is that the traditional barriers for data processing have been broken down. There's a lot of open questions, a lot of research, a lot of room for innovation, okay? Breaking down those barriers doesn't come for free. You give up guarantees, you give up performance. How do you get those back? And I kind of told you the directions that we're headed in, okay? So that's all I have. Thanks for your patience. If we have time for a question or two, let me know, and there's our website if you want more information.
Maybe take two brief questions if folks have something they'd like to ask.
Hi, good morning, Mike. Good stuff. Steve Muir from Comcast. I'm interested in sort of like a kind of a meta question maybe. One thing you didn't talk about, and I think this reflects what you guys have been doing, you don't talk about things like, programming languages or, low-level traditional systems stuff. So I'm kind of curious about whether you've found that to be, I know some of you guys have traditional systems backgrounds. Has that been a hard sort of cultural change? You kind of alluded to this at the end when you talked about single node performance. Exactly. Yeah. But it does sort of reflect the enterprise world, right? Enterprise has adopted Java, and I think sometimes the research community is sort of surprised when we find that out. But you mentioned Scala. Spark is Scala, right? Yep. Can you sort of comment sort of generally, what that has meant? And have you, I guess the main thing is, have you gotten benefits from not worrying about, C++ micro-optimizations and language this, and do you get the high-level language stuff?
Yeah. Okay, well, so that's a great question. And you're right that when I was alluding to single node performance, that was part of what I was talking about, is there's a bunch of things you can think about optimizing on a single machine that frankly we haven't thought too much about. Where you start running into the need to worry about some of these low-level language things is when you start benchmarking against some other systems. And in particular, the Impala system that Cloudera is building for their SQL processing is written in C++, I believe. And there are definitely queries where they run a lot faster because of that. But we're finding a couple things. One is we're finding that the just-in-time compilation actually works really well, and there are certain tricks you can play with the code to avoid a lot of the overheads of the JVM. And so we think we're able to get pretty close to kind of native, at least C++ type performance. And what we're finding is we're going to be able to add functionality much, much, much faster. And so I showed that graph with the lines of code. One of the reasons our lines of code are so small is because we're writing in a higher level language, and it just lets us move incredibly fast. So, I think that there probably will be a little bit of a performance hit on a single node basis, but not as much as people traditionally think there's going to be. But you have to do some smart engineering to get rid of those. But the benefit in being able to move fast, which is so important in this space as things are moving so quickly, I feel like we made that right decision, even if we didn't spend a lot of time agonizing over it.
All right, one thing I realized while Michael was talking was he has that initial graphic he pointed out, the difference between the cost of processing versus the cost of analyzing genomes. May have seemed a little spurious at the time. But one of the things that's really interesting about this work is it's all grounded in real applications. So I would encourage you to go look at some of their work. You'll see that they're doing a lot of analysis in the context of the real world, whether it's traffic monitoring or genomics analysis. They're consulting with the right domain-specific people in order to make a real impact on the world. I assume Michael will stick around during the break, and you can ask additional questions if you like. So maybe we can thank him one more time.